Today we're talking QM, AM, GM, HM. That's gonna be awesome. Okay guys, QM, AM, GM, HM inequality is a system of inequalities that happens to occur between means of real numbers. So it states that the quadratic mean, which abbreviated is QM, which looks something like this. Those are the numbers that we want to take the average of. I would like to call them xi's, let's say. Then we go on and square each of those numbers, then we add them up together. Then we divide the entire sum we just got by the number of the by the size of the sample. So the amount of numbers that we are taking the average of, and then we are taking the square root of those numbers. And it's supposed to be greater than or equal to the arithmetic mean, which abbreviated is AM, which is just the regular mean everybody knows, which is the sum of the numbers we're trying to take the mean of divided by the amount. And this arithmetic mean is supposed to be greater than or equal to the geometric mean, which is abbreviated GM. And so that mean is the product of all of the numbers we want to take the average of, and we take the nth root for any numbers that we take the product of in this kind of mean. So we just go on, take the product, and then we take the root of the degree of the amount of numbers that take part in the product. So the nth root of x1 through xn. And that's supposed to be greater than or equal to the harmonic mean, which abbreviated is HM, which is just the amount of numbers we take the average of divided by the sum of the reciprocals. So n divided by 1 over x1 plus 1 over x2, and we are just adding stuff until we get to 1 over x sub n. So the plan for today's video is to go on and prove this guy out. So this inequality right over there, and also this inequality right over there. We're not gonna be proving the QM-AM inequality because that's something I would like to leave for the Cauchy-Schwarz inequality video. So we're only going to prove the inequality between the arithmetic and geometric mean and the geometric and harmonic mean, and then we'll do some problems using those to get the sense of how to use those in problem solving. Awesome. Let's go. Okay guys, so the first proof we're going to be conducting is the proof of AM-GM inequality, and we would like to do this one by induction. However, not the regular induction. We would like to use a special type of induction, which is called, I'm going to use the word induction for the fourth time this time, the Cauchy induction. So a proof conducted by Cauchy induction looks something like this. First of all, we have to prove the base case, which is going to be always for n equal to 2 is fixed in this kind of induction. And then what we do is, well, as always, we assume that the semi will hold for some particular number k. However, what we do is we don't prove using this assumption that it will hold also for the number consecutive in that set to the number we assumed it for. However, we prove that the semi holding for k will imply that the semi will also hold for double the k. And then we do a second induction step, which is that k, the statement holding for k, will imply the statement holding for k minus 1. And this will actually prove the statement for all of the even numbers and all of the odd numbers. Well, that kind of covers all of the natural numbers. So, well, that's pretty perfect. That's exactly what we would like to do right now, right here. Okay, so what does the AM-GM inequality state? It states that whenever we have some numbers x1, x2 through xn, let's say, that are positive reals, we can say that the arithmetic mean, which is the sum divided by the amount of numbers we have, so n, is greater than or equal to the product but under the nth root. Lovely. So we would like to prove this one using Cauchy induction right over here. So let's go on and do this. First of all, we have to achieve the base case scenario. The base case is going to be for n being equal to 2. So first of all, the base case for n being equal to 2. Whenever we have two numbers, let's maybe call them a and b, because why not? We would like to prove that a plus b all over 2 is greater than or equal to the square root of a multiplied by b. Lovely. So let's go on and just prove both sides. Oh, sorry, then square root. Not prove, no, square root, square both sides of this inequality, getting a squared plus b squared plus double ab all over 2 being greater than or equal to ab. Now let's go on and multiply both sides of this inequality by a factor of 2, and maybe then we will just go on and kind of subtract ab from both sides of this inequality, getting a squared plus b squared being greater than or equal to 0. As a resulting inequality. Well, this guy is always true because a squared and b squared are always positive, or 0 if they are both 0. Yeah, so that's awesome. Our base case is checked. So now for the inductive step, sorry, for the assumption, we would like to assume that we will have a natural number k such that x1 plus ... plus xk all over k is going to be greater than or equal to the product of those k numbers under the kth root. Lovely. And so, well, for some k that is inside of natural numbers. Lovely. And I would like to conduct the first inductive step, so the inductive step, however, the inductive step number 1. Lovely. So for the inductive step number 1, we would like to prove that the statement holding for k will imply the statement holding for double decay. Awesome. So we would like to go on and see what will happen if we take the average of not k numbers but double decay numbers. And so we're going to be just adding stuff from x1 up to x sub double decay. We are going to go on and divide everything by double decay and see what is this stuff greater than or equal to. Well, actually, we can't really see anything right now, but let's try and manipulate this expression a little bit. For example, we could go on and distribute this k right over there somewhere into the numerator, so, you know, elevate it a little bit in this fraction, getting x1 up to xk all summed up all over k plus another similar looking fraction, so x sub k plus 1, and we're just going to be adding stuff until we get to x sub double decay all over k, and now all divided by 2. Those two guys are equal. But the nice thing is that now here as well as here we just have k numbers which we divide by k. And so this is exactly the case we had here in our assumption. And so we can just go on and say that those guys are going to be greater than or equal to, well, the square root, the kth root of the product x1 through x sub k plus the kth root of x sub k plus 1 through x sub double decay, and all over 2. This line is not perfectly straight, but yeah, now it's better, I think. Lovely. No, it's not better. Now it's better. So this was by the assumption. However, right now I would like to see one more thing. Well, those k fruits of some product of some numbers are just, well, real numbers. Those are not expressions in terms of any variable. Those are just numbers. And so whenever we have two numbers added together and divided by 2, well, they're greater than the square root of the product. I mean, by the base case we did. Okay, well, that's pretty nice, because now we can just go on and say is greater than or equal to the square root this time, so I'm not even writing this 2 down right here, of the kth root of x1 multiplied by all of the x's through k, and then multiplied by this kth root, this time I stopped myself, x sub k plus 1 through x sub double dk, and well, the square root of the product of those kth roots is just gonna be equal to the double kth root of the product of all of those numbers from x sub 1 up to x sub double dk. I'm not good at writing. I'm drawing straight lines, I'm gonna be honest with you guys. And so this is exactly what we wanted to prove for the first inductive step. So we see that the statement holding for k does imply the statement holding for double dk. However, what about the case for this, about the second inductive step? So now number 4, inductive step number 2, and so the statement holding for k implies the statement holding for k minus 1. Lovely. So we already covered the powers of 2. Now let's go for the odd numbers. Lovely. So we once again just assume that this statement will hold for k. How do you prove it's going to hold for k minus 1? Well, I would like to show you guys a really neat trick. So let's first of all go on and write down the sum, the arithmetic mean of those k numbers. What can we do to make it look more like an arithmetic mean of k minus 1 numbers, honestly? Well, what we can do is say that our xkth numbers, so our x sub k, is going to be equal, so I'm going to maybe write it somewhere here. I would like to say that x sub k is going to be equal to the arithmetic mean of all of the remaining numbers. And well, can I do that stuff? I absolutely can, because I'm not even trying to take myself any particular values for those x's. This is not an equation right now. What I'm doing is I'm just kind of shifting some numbers. I'm just subtracting some stuff from those numbers, x1 through x sub k minus 1. And just, plugging those into the x sub k, so that x sub k will eventually be equal to the arithmetic mean of all of the rest of those numbers. And well, is it going to change the final value of this entire fraction? Well, absolutely not, because I'm still going to add all of those numbers up in the numerator and then divide them up by k. Doesn't change a thing. So I can do it. I can just go on and plug this stuff right here. And so what I'm getting is the sum of all of those x sub i's until the x sub k minus 1 plus x1 plus ... plus x k minus 1 all over k minus 1, and now everything once again over k, not k minus 1, but k. Lovely. This doesn't look like a k. Now it's not better, but whatever. So, well, what can we do now? What we can do is just get those two to a common denominator, let's say. So what I can do is multiply this guy right here by k minus 1 and get this k minus 1 here to the denominator. So let's do it. What we're gonna get after this kind of a transition is, well, k minus 1 multiplied by the sum of all of those k minus 1 x's here, then plus x1 ... xk minus 1, and everything is going to be divided by k multiplied by k minus 1. However, you see, The nice thing is that here we've got x, the sum of all the x's from x1 up to xk minus 1, and here we have, well, just the same thing, however, it's multiplied by k plus 1. So you can just go on and add those things together, or if you prefer to think of it that way, we can just go on and factor the sum of all of the xi's away, getting x1 plus dot dot plus xk minus 1 multiplied by k minus 1 plus a 1. And so what we're gonna get is k multiplied by the sum of all of those k minus 1 x's divided by k times k minus 1. But, well, those two k's right here are gonna just beautifully cancel each other out. And so we will be eventually left with just the arithmetic mean of x sub k minus 1 numbers without a doubt. And that's really what we were after here. Okay, lovely. So after this kind of a transition, what can we do with all of that stuff? Well, we know that the arithmetic mean of the k numbers is equal to the arithmetic mean of the k minus 1 numbers. However, by our assumption we made earlier, the inductive assumption, the inductive hypothesis, applied to the arithmetic mean of k numbers. But now, well, it's equal to the arithmetic mean to k minus 1 numbers, so the inductive hypothesis has to apply to the arithmetic mean of k minus 1 numbers because it's equal to the arithmetic mean of k numbers. I will show you guys what I mean in a second graphically, let's say. So we know by our assumption that x1 dot 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 plus x sub k all over k is greater than or equal to the kth root of x1 multiplied by all of that stuff through x sub k. However, this guy right here is actually going to be equal to the arithmetic mean of all of those k minus 1 x's. And so we see by all of this stuff that the arithmetic mean of k minus 1 x's is going to be greater than or equal to the kth root of x1 through xk multiplied together. Okay, but, well, it's not really what we wanted here. So what can we do? Oh no, what happened? What can we do to this poor root right here to make it look a little bit more like the thing we want it to look like? So we're just gonna plug, just a second, I'm just gonna rewrite this thing here. Okay, we would like to plug in this value for x sub k to this x sub k right over here. So what we're gonna get is that the arithmetic mean of k minus 1 numbers is gonna be greater than or equal to the product of first k minus 1 numbers, and it's multiplied by x sub k is equal to, well, the arithmetic mean of the k minus 1 numbers. Yeah, and it's all going to be under a kth root because the degree of the root is not changing at all. But what can we do now? We can just go on and raise both sides of this inequality to the kth power, and there will be no problem in doing that. So the arithmetic mean of those k minus 1 numbers, all divided by k minus 1, everything to the power of k is greater than or equal to the product of the k minus 1 numbers multiplied by the arithmetic mean of the k minus 1 numbers. Okay, but the nice thing is that those two guys right here, so him and him on behalf, sorry, those guys are equal to each other, and so we can just go on and divide them out from both sides of this inequality, getting that the arithmetic mean of those k minus 1 numbers to the power of k minus 1 is greater than or equal to the product of those k minus 1 numbers. Now just take the k minus first root and you're done with everything you're supposed to be done with. And so this is the proof of AMG. And what did we do here? Well, we used the Cauchy induction. First of all, we considered the base case of n being equal to 2. Then what we did is we make an assumption that our statement will hold for some particular natural number. We call that number k. Then we did the first inductive step. We proved that the statement, well, assumably holding for k will imply the same in holding for double decay, what we did exactly right over here. And then we did the second inductive step, so that the same in holding for k will imply the statement holding for k minus 1, assuming that x sub k is equal to the arithmetic mean of all of the other x's, which is something that we absolutely can do just by kind of shifting value right over here to this x sub k. The product doesn't change, so nothing changes here. And we managed to prove that the statement holding for k will imply also the statement holding for k minus 1, which completes our inductive proof, and also the proof 1, which was to prove the AMG inequality. Let's move on to the proof number 2. Okay guys, so for the proof number 2, what can we do here? Well, the only proof we are left with is the proof of GMHM inequality, because I said the QMAM we're going to be proving in the Cauchy-Schwarz video, and so let's go on and prove this inequality. Lovely. So how are we supposed to do it? Well, let's first of all try and recall what did that inequality even state. Yeah, so that was that the product of sum and numbers that is under n, the nth root is greater than or equal to n over the sum of the reciprocals of those numbers, so that the geometric mean right over there is greater than or equal to the harmonic mean right over here. So this is our statement. We would like to do this one not by induction this time. I would like to actually drop the pen. So we would like to this time do this one with a neat trick. We would like to substitute in for our x's a newly defined sequence. I would like to define myself a sequence a sub i's. Yeah, so a sub i's are gonna be equal to the reciprocals of the x sub i's. And if I do this thing, then I will notice that the statement I had here is gonna drastically change into something like this. Let me first of all rewrite the original statement. Okay, right over here. So it's gonna change into something like this. The nth root of the product of all of the xi's is gonna change into the reciprocal of the product of all of the xi's. Actually, sorry, the reciprocal of the product of all of the ai's, but it's gonna be still under the nth root, and it's supposed to be greater than or equal to n divided by the reciprocals of x's, so that's gonna be a1 plus ... up to an. And so actually see that this thing right here is just AMGM, but quite flipped upside down, yeah? We can just go on and erase both sides here to the -1 power, yeah, to the -1 power, and get, by doing that, that a1 ... up to an all under the nth root is supposed to be less than or equal to a1. We're going to be just adding stuff until we get to the nth a divided by n, but this is just the AMGM inequality, which we proved just a few seconds ago. And this is, ladies and gentlemen, the perfect proof of this inequality. That was quick on how, yeah, it was 3 minutes and 5 seconds, so I think it's a perfect time to go on and solve some problems. Okay guys, so for the first problem we would like to prove that the sum of some real numbers, positive real numbers xi's up to x sub n multiplied by the sum of the reciprocals is always greater than or equal to the squared amount of those numbers, so n squared this time. Well, there's actually a problem which is supposed to be pretty clear, and just to remind you guys how those inequalities we just proved worked. Okay, so, well, we see that if we were to divide both sides of this inequality by n, and to also divide both sides of this inequality by the sum of the reciprocals, what we're gonna end up with is x1 plus dot 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 up to x sub n, everything divided by n is greater than or equal to n divided by 1 over x sub 1 dot 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 plus 1 over x sub n. And you see, nice thing is that this thing right over there is actually the arithmetic mean, and the guy right over here is actually the harmonic mean. But well, we know that the arithmetic mean is greater than or equal to the geometric mean, which is greater than or equal to the harmonic mean. And so it, well, by definition, will mean that AM, so the arithmetic mean, is also going to be greater than or equal to the harmonic mean, which directly implies the problem statement we were supposed to prove. Yeah, so that will be all for it. Let's go to the second one. Okay guys, so for the second problem, we are supposed to take a1, a2 and an such that all of those a's are positive reals, such that the product is equal to 1. We're supposed to prove that 1 plus a1 times 1 plus a2 all the way to 1 plus an is greater than or equal to 2 to the power of n. Perfect. Lovely. So how are we supposed to solve this problem? Let's consider each and every one of those guys right over there separately. So we see that 1 plus a1 is by AMGM greater than or equal to double the square root of 1 multiplied by a1, which is just a1. Okay. We see that 1 plus a2 is greater than or equal to double the square root of 1 plus a2, which is a2. Lovely. We can just go on and keep doing it as long as we want until we will eventually hit 1 over a sub n, which is going to be greater than or equal to double the square root of a sub n. Lovely, because now what we can do is just go on and multiply all those guys out. There's no problem in doing that, to get the product of 1 plus a1 times 1 plus a2 times dot dot dot. We're going to be just multiplying stuff until we get to 1 plus a sub n is going to be greater than or equal to 2 to the power of n times the square root of a1 multiplied by all of the stuff up to an. However, we know by the problem conditions that the product of all of those numbers is equal to 1, and so, well, the square root of this product is going to be just square root of 1, but the square root of 1 is just a 1, so this right hand side is going to be equal to 2 to the power of n. This is exactly what we wanted to achieve in this problem. We are breaking speed records here. It was 2 minutes and 7 seconds for this problem to be completed. Lovely. Let's go further. Okay guys, so the problem number 2, we're supposed to prove for a, b, c that are positive reals that a cubed over bc plus b cubed over ac plus c cubed over ab is greater than or equal to the sum of a, b and c. Lovely. Okay, so how the hell are we supposed to do this one? I'm surely not multiplying everything out here because I'm just too lazy for that. You know, math is for lazy guys. Absolutely obvious stuff, though. So, well, let's just kind of remind ourselves about the AMG inequality. So it states that whenever we have some positive numbers, let's say I have 3 numbers for this matter, some 3 positive real numbers, yeah, I divide them by 3 after summing them up. That's going to be greater than or equal to the cube root of the product. Okay, that's lovely. How can I leverage that in this problem? When I see that here I have this b multiplied by c in the denominator, how can I get rid of this stuff? Well, if I go on and say add a cubed over bc plus b plus c, yeah, what I'm gonna get is that this is actually gonna be greater than or equal to the cube root, or maybe I shouldn't have written the cube root yet. A cubed over bc multiplied by b and multiplied by c, and now the cube root applies. Okay. But those two cancel each other out. So this is gonna be just equal to the cube root of a cubed, which is a. Okay. Oh, sorry. Triple the cube root and triple the a, because I did not divide those guys by 3 here. Sorry. But this means I can do just the same thing with with every single fraction that I'm left with. So let's just say that b cubed over ac, I will add myself an a and a c, is going to be greater than or equal to just 3b, and c cubed over a times b, that's going to be plus a plus b, it's going to be greater than or equal to triple the c. And so the only thing I actually really have to do to this inequality, so a cubed over bc plus b cubed over ac plus c cubed over ab greater than or equal to a plus b plus c, is just add b plus c, then a plus c, and then a plus b to both sides of this inequality. So I'm gonna get here is just, well, a cubed over bc plus b plus c plus, or I'm not really writing it perfectly straight, am I? I guess being laid back is not the best option at all times. Though sometimes it is, but maybe not at this particular moment. So plus a plus c, and then plus c cubed over a times b plus a plus b is supposed to be greater than or equal to triple the a plus triple the b plus triple the c. But the nice thing is that this guy right here is gonna be greater than or equal to triple the a, so the guy right over there. This guy is gonna be greater than or equal to triple the b, so the guy right here. And this guy right over there is gonna be greater than or equal to triple the c, so the guy over here. And so we see that if we sum those guys up, it is clear that this entire thing is going to be greater than or equal to the right hand side, and so we have our inequality proven. So what did we do here? We thought how to leverage AMGM inequality in this problem. We figured out that if we added the sum of the numbers that are multiplied in the fractions denominator to the given fraction, then that fraction is going to be greater than or equal to the number, to triple the number that is here in the numerator. And so we did that stuff and it turned out that it quite nicely proves our inequality. So that would be all for problem number 2. Okay guys, so the problem number 4, we're supposed to minimize x squared plus y squared, where x and y are positive real numbers, given that x plus y is equal to 10. Lovely. So what does it mean to minimize something? It means to find a number, a real number k, such that the expression we are supposed to minimize cannot be smaller than that. So such that x squared plus y squared is greater than or equal to k. This means that we minimized x squared plus y squared and the lower bound is k. Perfect. So how are we supposed to do it? Let's first of all find a way to link x squared plus y squared with x plus y. Well, how can we do it? We see that x plus y squared is equal to x squared plus y squared plus double xy. Okay, that's lovely, because we see that x plus y is equal to 10, and so 10 squared, well, that's 100. And so we thus see that 100 minus double xy is equal 2x squared plus y squared. Well, we are close enough, because now we see that the only remaining thing that we have to deal with is double xy. However, this we can deal with using the AMGM inequality, because we see that x plus y over 2 is greater than or equal to the square root of x multiplied by y. However, x plus y, well, that's a 10, and so we see that 5 is greater than or equal to the square root of x times y, which means that 25 is greater than or equal to x multiplied by y without the square root anymore. And so we see that since 25 is greater than or equal to x plus y, and so x plus x times y is less than or equal to 25, then double the xy is less than or equal to 50. And so this thing will be at least 50. This thing's gonna be at least, this thing's gonna be at least 50. And so we see by this thing that since x squared plus y squared is equal to 100 minus double xy, which is at least 50, we see that x squared plus y squared is at least 50, and this is exactly what we were supposed to find. I mean, this 50 right over there is such that, well, x squared plus y squared cannot be smaller than that, and so we managed to minimize x squared plus y squared. Okay guys, so to wrap it up, we have this inequality. It's called QMAM HM, is between the quadratic mean, the arithmetic mean, the geometric mean, and the harmonic mean, where the quadratic mean is the greatest and the harmonic mean is the smallest of all of those. We covered two proofs, so the proof of AMGM and the GMHM. We will prove the QMAM in the episode on Cauchy-Schwarz. We did 4 problems. I showed you how to use AMGM to maximize stuff, and also how to use it to get rid of some fluffy nonsense, as in the example of a cubed over bc and stuff like this. And well, if you want to see more examples of how to use those inequalities to solve problems, well, then just keep track of the rest of my videos, because I will be posting stuff regularly there. And I'm sure I will post something on AMGM or QMAMGM HM for sure. So thank you guys for watching. I hope you enjoyed it, and see you in the next one. Bye.